Hello everyone, welcome back to this online class. Today we are going to look at how to solve ODEs of the first order and first degree. And in particular, we're going to look at separable ODEs. Now we are given three questions to solve. The first one is x dy over dx is equals to y plus y squared. And the condition is that y when x is 1 is equals to -2. Part B, we are given x plus y plus 1 dx minus 2y plus 3 plus 2x dy is equals to 0. And in part C, we are given cosine of x plus y dy is equals to dx. So we need to find the solutions of each of those equations. Remember, each of these equations is separable. So let's start with part A. Solution for part A. We are going to write part A. Of course, we need to separate the variables. When we talk of separating the variables, what it means is that you collect the dy's, the y's and the dy's on one side, and the x's and dx on the other side. So if you look at this equation, how can we separate the variables? Let's see. I am going to multiply through by dx. So when I multiply through by dx, I'm going to get x dy is equals to y plus y squared dx. I have multiplied the equation by dx. Now you see I can now divide, because I want to get rid of y plus y squared from here, because here I have dx. So I'm going to take this x here. I'm going to divide the equation by x so that I have it here. And also this one, the y plus y squared, you take it to the left-hand side. So that means I'm going to divide by, you can write divide by x times y plus y squared. So what are we going to get upon division? So that means we are going to get x dy over y plus y squared times x is equals to y plus y squared dx over x into y plus y squared. So that we can now be able to simplify. This will cancel. All of this will cancel with this. So this simply means that we have dy over y plus y squared is equals to dx over x. So this is now separable. You see, we have managed to collect the x's and the dx on one side, the y's and the dy's on another side. Or this thing can as well be written as, or dx over x minus dy over y plus y squared is equals to 0. So then once you separate the variables, the next step is to integrate each term separately. Now, let's start by integrating dx over x. The integral of dx over x, that is equals to the same as the integral of 1 over x dx. What did you differentiate to get 1 over x? That was again x, natural log of x. Now that's the first term. Let's also integrate this, the integral of dy over y plus y squared. This can also be written as the integral of 1 over y into 1 plus y dy. Now, how do you integrate when the denominator is a product of two linear factors? You see, y is a linear factor, 1 plus y is also a linear factor. So to be able to integrate this, you have to use partial fractions decomposition. So you're going to say let 1 over y into 1 plus y be equal to a over y plus b over 1 plus y. So that our task here is to find the values of the constants a and b. Now, if I cross multiply, or simply if I multiply the whole of this equation by the LCM, our LCM here is y times 1 plus y. So when you multiply that equation by the LCM, you're going to get, let's start with the right hand side, a times 1 plus y plus b times y is equals to 1. So this equation is true for whichever value of x that you choose. Not x, but y. That in this case it is y. So whichever value of y that we choose, that equation will be satisfied, will be true. It's advisable that you choose values of y which are very close to 0 and which will help eliminate some terms on the left-hand side. Of course, there are two ways of finding a and b. The first method is elimination method, and another method is when you compare the corresponding coefficients on the left and also right-hand side. But I want to use the elimination method to realize that if I put y is equals to 0, I'm going to get, because now we'll now have a into 1 plus 0 plus b times 0. Let me take this to the left. B times 0 is equals to 1. And you see, anything multiplied by 0 is 0. So b times 0, that this term will vanish. So here we only remain with a times 1 is equals to 1. So therefore, here you're going to get a is equals to 1. Again, you realize if I put y is equals to -1, the first term will disappear, it will vanish. So that means I'll have a, we just write everything, 1 minus 1 plus b times -1 is equals to 1. And you see, 1 minus 1 is 0, so we expect this term here to vanish, so that we have negative b is equals to 1, of which you can now make the b the subject, so that you get b is equals to -1. So we now know a and we know b. So I now replace them here. Instead of a, I'm going to replace by the value that we have found, and instead of b, we replace by the value that we have found. So here it is 1, and here it is -1. So now we can come back to our integral. So this integral can now be written as the integral of 1 over y minus 1 over 1 plus y dy. So that when you interpret the first term, you get natural log of y. The second term will give you natural log of 1 plus y. That's what you get on the left-hand side, the second term. And you see, you can combine these two natural logs using the laws of logarithms. Let me write for you the laws of logarithms. Take note that when we talk of log A plus log B, this can always be written as log of A times B. That's the first law. Another law is log A minus log B. This you can write as log A over B, second law. And the third law is M log A can be written as log of A raised to M, third law. So those laws are very important. So here we need to combine this and also this, and there's a minus, so we are going to divide them so that this answer can now be written as natural log of y over 1 plus y. Finally, on the right hand side, we have the integral of 0. What is the integral of 0? You see, you are told in calculus 1 or differential calculus that when you differentiate a constant, you need to get 0. So now the opposite. What do you get when you integrate 0? We need to get a constant c. This is a constant of integration. So therefore, let's replace our answers. The first one was this on the left. Another one is this, and on the right we have c. So we are going to now to say that this one gave us ln x. This other one gave us minus ln y over y plus 1. Let me have 1 plus y. 1 plus y. And the other one is a constant. You see, instead of having to write c, because you see on the left hand side we have natural logs, each of them, you could even write this one as ln c instead of just c. So get rid of c and write as ln c. It's better if it is a natural log too. So here you also write ln c, so that we can easily apply the laws of logarithms to eliminate those logs. So on the left, when you apply the laws of logarithms, this can as well be written as ln x over y into 1 plus y, this one, is equals to ln c. And here we have this. So now when you take exponential on both sides, what are we going to get? This you can say or, and finally, we are going to say x over y over 1 plus y is the same as a constant of integration, which you can as well write as, if I cross multiply, you can say or x is equals to c times y over 1 plus y, or x into 1 plus y is equals to c times y. This is our general solution. So what you have found here is called a general solution. Let me bracket it again. So you can write this is general solution. Remember, there's a difference between general solution and particular solution of an ODE. When you talk of general solution, it is a solution or simply the primitive that is associated with the ODE. That solution that has arbitrary constants. Of course, they are essential arbitrary constants. Now, when you talk of particular solution, it is what you get from the general solution when you know the value of the arbitrary constants. And how do you know the values of those arbitrary constants? You need to apply the initial conditions to be able to get the values of those arbitrary constants. And so once you know their values and you replace them into the general solution, what you get is called particular solution. So look at our question. We have found our general solution, but again we are told that we need a solution that is subject to the condition that when x is equals to 1, here. This is the value of x. When x is equals to 1, y should be equal to -2. So this means when x is equals to 1, comma, it means that y should be equal to -2. So this condition will help us find the value of the arbitrary constant c. So let's apply that. So you can write here, apply the condition that y when x is 1 should give us -2. So that means you put x is 1 and y is -2. This means put x is equals to 1 and y is equals to -2. So what are we going to get when you make such substitution? So we are going to get, on the left we have 1, which is x, then 1 plus -2, which is y, is equals to c times -2. You can now make c the subject, so you can write or. Here we have, what do we have on the left is -1 is equals to -2c. That's what we have. Make c the subject, so this means that our c is equals to, that is now we divide by -2, so that will give us 1/2 as the value of c. Now when you replace it back to the general solution, we get the particular solution. So you say therefore x into 1 plus y is equals to 1/2 times y. So what we have here, we bracket this. This is called particular solution. So now I have explained what we mean by general solution and particular solution. Now let's find the solution of equation B. So I'll take you up to where we have equation in part B. It is x plus y plus 1 dx minus 2y plus 3 plus 2x dy is equals to 0. So I'm going to write that. Part B. X plus y plus 1 dx minus 2y plus 3 plus 2x dy is equals to 0. So again, this is separable. Remember, this equation can be rewritten as, x plus y bracket, then plus 1 dx minus, remember 2y plus 2x can be written as 2 into x plus y. Because I can see 2 is common, then there is 3 dy is equals to 0. So look at the common factor. I can see x plus y is common in each term. So that common factor, you let it to be equal to u. This kind of an ODE is an equation that is separable, but you can only separate it once you make a certain substitution. So this reduction to separable ODE. Now we are going to say let x plus y, because it is common, it's a common factor. So we'll say that let u be equal to x plus y. So that where this x plus y, we are going to write du. So this means that du dx is equals to 1 plus dy dx, differentiating both sides with respect to x. Now, if you multiply both sides by dx, you are going to get du is equals to dx plus dy. I've multiplied both sides by dx, both sides of this equation by dx. And now make dy the subject. So you can say or dy is equals to du minus dx. So these are the substitutions. This one, where there is x plus y, we write du. And also this, where there is dy, we are going to write du minus dx. I said where there is x plus y, we are going to write u. And where there is dy, we're going to write du minus dx. So therefore, our ODE, when we substitute these two, we are going to get u plus 1 dx minus 2u plus 3. Instead of dy, we replace that by du minus dx. And that should give us 0. Or this can be written as u plus 1 dx minus 2u plus 3 du plus 2u plus 3 dx is equals to 0. The next thing is to combine like terms. You see this and this are like terms. Let me combine them. So you can say or u plus 1 plus 2u plus 3. This is the coefficient of dx minus 2u plus 3 du is equals to 0. And so I can simplify. Look at the coefficient of dx. If you simplify, you are going to get, let's say, or 3u plus 4 dx minus 2u plus 3 du. This should give us 0. Now, this equation is separable. It is possible to collect the x's and the dx on one side, the u's and the du's on another side. So you can write this is separable. It is a separable ODE. Now let's separate the variables. I'm going to collect the u's on one side and the x's on another side, including dx and du. So you can just say, or when you separate the variables, you're going to have dx minus 2u plus 3 over 3u plus 4 du. And that should give us 0. So once you separate the variables, just like we have done here, then you can now integrate each term separately. Now the question is, how do you integrate those terms? So I'm going to work them out here. The integral of dx is the same as x. It's just like integrating one with respect to x. Or simply you see integral and derivative are inverses of each other. So when you cancel those, you remain with x. Now, the other one, the integral of 2u plus 3 over 3u plus 4 du. Now, what do we do here? Look at what we have in the numerator and what we have in the denominator. You realize that each of them are polynomials. In the numerator, it is a polynomial of degree 1. In the denominator, it is also a polynomial of degree 1. When the degree of the polynomial in the numerator is equal to or greater than the degree of the polynomial in the denominator, then first of all, you have to use long division process to simplify the integrand. So I'm going to long divide so that I see what I'm going to get, because I cannot integrate the way it is. I have to simplify that integrand to make my work easier when integrating. And why are we using long division? Is because in this case, the degree of the polynomial in the numerator is the same as the degree of the polynomial in the denominator. So you're going to say that you're using long division. Long division, so we have 3u plus 4. Here we have 2u plus 3. So you need to ask yourself, what do you multiply by 3u to get 2u? The answer there is 2 over 3. That's what you multiply by 3u to get 2u. So 2 over 3 times 3u, that will give us 2u. And then 2 over 3 times 4, we get 8 over 4. No, 8 over 3, I mean. Now we subtract the 2. 2u minus 2, that is 0. 3 minus 8 over 4. Same, remember, 3 is the same as 9 over 3. Then minus 8 over 3. That will give you 1 over 3. So it's like this integrand can now be written as, you can just say that therefore, where you have 2u plus 3 over 3u plus 4, you can now write this as 2 over 3. Let me check this up. That you can write as 2 over 3, remainder 1 over 3 divided by 3u plus 4. So we have simplified. So therefore, you can now say that this integral is now equal to the integral of 2 over 3 plus 1 over 3 over 3u plus 4 du, which you can write as the integral of 2 over 3 du plus 1 over 3, the integral of 1 over 3u plus 4 du. So how do you integrate 2 over 3 with respect to u? You get 2 over 3 u. Plus, here you're going to use another substitution. Maybe let z be equal to 3u plus 4. So that when you integrate that and multiply by 1 over 3, you get 1 over 9 ln 3u plus 4. And finally, the integral of 0, should give us a constant c. So look at our answers. This is the first answer, the second, and this is the third. Now we go back to our problem. Here we got x minus, here we have found this bracket 2 over 3 u plus 1 over 9 ln 3u plus 4. On the right hand side, we have found a constant c. So that is our general solution. But remember, you need to replace u because we need to go back to x and y. So you need to put u is equals to x plus y. So therefore, we now be talking of x minus 2 over 3 into x plus y minus 1 over 9 ln 3x plus 3y plus 4 is equals to a constant c of integration. So what you have found is the general solution of the given ODE, where c is an arbitrary constant. Let me bracket this solution. Remember, here we cannot find particular solution because we are not given the condition to apply. So what you have found here is the general solution. Finally, in part C, we need to solve cosine of x plus y dy is equals to dx. So let me write it here. In part C, we have cos x plus y dy is equals to dx. That's what we have. So what do? We are going to make a substitution again here, because you see the way it is not easy to work it out. So we are going to say let x plus y be equal to u. Let me start by saying let u be equal to x plus y. So when you differentiate both sides by simply with respect to x, we are going to get du dx is equals to 1 plus dy dx. If you cross multiply by dx, we are going to get du is equals to dx plus dy. Or if you make dy the subject, you are going to get du minus dx. So that's what we have. We are going to substitute this one and also replace dy. These are the substitutions. So what will be our equation now in terms of x and u? So therefore our ODE can now be written as cosine of u dy is the same as du minus dx is equals to dx. And if you open the bracket, this is the same as cosine of u du minus cosine of u dx is equals to dx. And you see the dx is common, so this you could also write as, this is a separable ODE now. You could write this as cos u du is equals to cosine, let me start with the dx, is equals to dx plus cos u dx. I have taken this one to the right hand side, so that when you simplify this, we are going to get cosine of u du is equals to 1 plus cos u dx. So this equation is separable. This is separable ODE. Now we need to collect the x's and the dx on one side, the u's and the du's on the other side. So when you separate the variables, you're going to get cos u over 1 plus cos u du is equals to dx. That's what we have. Now, how else can we write this one? Cos u, you look at the left-hand side. If you divide numerator and denominator by cos u, you are going to get 1 over cos u plus 1, or simply 1 over sec u plus 1. But there's no need of dividing. What you do here, we are going to integrate both sides. Integrate here. You also integrate this. Now, how do you integrate the left-hand side? Let me work it out here. The integral of cosine of u over 1 plus cos u du. Every time you have trigonometric functions in the denominator, you use the t method of substitution. So here, we are going to say let t be equal to tan u over 2. So when you differentiate both sides with respect to u, so you get dt du will give us derivative of tan gives us sec squared of u over 2 times derivative of u over 2, which is 1 over 2. So now I need to make du the subject. So therefore, du is equals to 2 dt over sec squared of u over 2. And let us take a note here. This identity is very important, that 1 plus tan squared theta is equals to sec squared theta. So therefore, this can now be written as 2 dt over 1 plus tan squared of u over 2. That's what we have. But what is tan u over 2? We know it. Tan u over 2 is equals to t. So what is the square of that? Tan squared of u over 2, that will be t squared. So this is the same as 2 dt over 1 plus t squared. That is du. So this is a substitution that you're going to make where we have du, it is that, where we have, of course, we start by saying tan u over 2 is equals to t. I also need to know what is cos u in terms of t. So again, let me draw a right angle triangle. This one, so that the angle here is u over 2. Tan u over 2 is t over 1. So the opposite is t, and the adjacent is 1. Use Pythagoras theorem to get the hypotenuse. So the hypotenuse here will be the square root of 1 plus t squared. So that from here, we can get cosine of u over 2 from that triangle. Cos is adjacent of hypotenuse, that is 1 over root 1 plus t squared. And from the same triangle, you can also get sine of u over 2 from that triangle. opposite is t, hypotenuse is the square root of 1 plus t squared. That's what we have from that triangle. Now, what is cos u? Because that's what we need to find. Also, another identity that we need to take note of, we can write, you take note that cosine, let me write it the other side. So I'm going to rub this. Take note that cosine of 2 theta is the same as cosine squared theta minus sine squared theta. So that this now, when we need cos u, can say therefore cos u is the same as cosine squared of u over 2 minus sine squared of u over 2. And you see we have them, we only need to square this and this one. So let's square the cosine of u over 2. This is the same as writing 1 over root 1 plus t squared. The whole of this is squared, then minus t over root 1 plus t squared. The whole of this is squared. And so when you simplify, you'll get 1 minus t squared over 1 plus t squared. That is cos u. I also need 1 plus cos u. So I'll extend this. I now need 1 plus cos u, 1 plus cosine of u. That is simply 1 plus what you have found, 1 minus t squared over 1 plus t squared. And so this can be written as 1 plus t squared plus 1 minus t squared over the common LCM is 1 plus t squared. So you see here, the t squared will cancel with this other t squared, so that this will give us 2 over 1 plus t squared. So that's what we have. Now we can go back to our integral. Look at this integral on the left-hand side. Therefore, on the left-hand side, the integral of cos u over 1 plus cos u du. First of all, I needed to write cos u over 1 plus cos u. What is that? So let me find it here. We need to find cos u over 1 plus cos u. What is the answer? Cosine of u, we got 1 minus t squared over 1 plus t squared. We are dividing this by 1 plus cos u, which we have found 2 over 1 plus t squared. That's what we have found. And so when you simplify this, the denominator will cancel. You see, this will cancel with this. So what we have is simply 1 minus t squared over 2. That's what we have upon simplifying that. 1 minus t squared over 2. So now we go back to this integral and replace the whatever we have found. So this is the integral of 1 minus t squared over 2. Then du, we got this 2 dt over 1 plus t squared. So you see that the 2's will cancel. So we only now talk of the integral of 1 minus t squared over 1 plus t squared dt. The question is, how do you integrate this? In the numerator, it is a polynomial of degree 2. Denominator is a polynomial of degree 2. When the degree of the polynomial in the numerator is the same as the degree of the polynomial in the denominator, then first of all, use long division process to simplify the integrand. So long division, we are going to take 1 plus t squared. Then inside we'll have 1 minus t squared. So you ask yourself, remember this can be written as negative t squared plus 1. What do you multiply by t squared to get negative t squared? That is negative 1. Let me use another color. So negative 1 times everything here will give us negative 1 minus t squared. Then I subtract 1 minus negative 1 is 2. Negative t squared minus negative t squared, that is 0. So it means that this kind of integral can now be written as, it goes there 1 times, remainder 2 over 1 plus t squared dt. We have used long division. Now this can be written as the integral of 1 dt plus 2 times the integral of 1 over 1 plus t squared dt. And what do we get? It is t plus 2 tan inverse of t. Remember, for you to integrate 1 over 1 plus t squared, you're going to substitute, let t be equal to tan theta, so that when you work it out, you get tan inverse of t. Of course, these are integrals that you've done them in calculus too. So at this level, I expect that you should know all those techniques of integration. So let me give you the hint here. What I've done is to put t is equals to tan theta, so that when you work it out, you get that integral to be tan inverse of t. Now, we need to replace t because we are integrating a function of u. So replace t by tan u over 2. So here, put t is equals to tan u over 2 here. And it's another color that put. That's back substitution. That's what we are doing. T is equals to tan u over 2. Back substitution. So what will it give us? This will now give us tan u over 2 plus 2 tan inverse of tan u over 2. That's what we get. But you see, this can be simplified. Tan inverse of tan is an identity. So that's 2 times u over 2. So this you can write as tan u over 2 plus 2 times u over 2, which is simply u because the 2's will cancel. So this can be written as tan u over 2 plus u. You see what you have found? That is the integral of cos u over 1 plus cos u with respect to u. So what about the right hand side? The integral of dx is equals to x. And don't forget to write the constant c of integration. So this will give you x plus c. So we now go back and say therefore. We can just say that hence our solution is now tan u over 2 plus u is equals to x plus a constant c of integration. Now, but you look at our original problem was in terms of x and y. We only introduced u somewhere, so I have to replace it back so that I go back to x and y. So it means where there is u, here we are going to put x plus y. You must go back to the original variables. So you ensure you perform all the back substitutions that are necessary. So we are going to substitute where there is u, put u is equals to x plus y to get tan x plus y over 2 plus x plus y is equals to x plus a constant c. C is an arbitrary constant, a constant of integration. And so what you have found there is our general solution. What do you realize? That the x will cancel, so that we have this x will cancel, this x will cancel with this, so that we now talk of therefore, or simply or tan x plus y over 2 added to another y should give us a constant c of integration. So this one here is our general solution. General solution. I already explained the difference between general solution and particular solution. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in ODEs of first order and first degree. Bye bye.